Hi guys, welcome to my YouTube channel Codes of Fun. Today we are going to see Leetcode problem number 668. Create the smallest number in a multiplication table. So there is a multiplication table of size m cross n in an integer matrix mat with mat of ij is I into j. So it contains m rows and n columns. We should find the kth smallest element, and each element is just multiplied by both of the indexes, like I cross j. So let me explain you. So if there is a if there is a problem, if there's m equal to 3 and n equal to 3 means there will be 9 elements, and each will be just multiplied by, if this is 1 2 3 1 2 3, this will contain 1 2 3 2 4 6 3 3 6 9. So yeah, this is the matrix. It will always be multiplied by I into j. So they have asked us the kth smallest element. So given it is always be in a sorted order. That is the first observation we saw. So when there is a matrix given and they are asking the kth smallest element or something. So basically what we can straight away do is go through all the elements in the matrix, and when the count go through all the elements in the matrix, store it in a external array or something, sort it, and find the kth smallest element. This will cost a time complexity of m cross n. That will give a TLE in this case. So we need something faster than this. As we can see, all the rows are sorted. So the first observation we can do is we can try binary search. So first we should do binary search in each of these rows in order to find number of elements smaller than that element. So first we are going to start off with the what is the maximum possible number. What is the maximum possible number in this matrix is that is m into n. That is m into n. And what is the smallest possible element is 1 into 1. That is 1. So we need to find a number between 1 and m into n, which is present in the matrix, such that including that the total number of elements, that is the total number of elements smaller than that or equal to should be k. So first we can start off by doing a binary search over this range given to us. As I told, the range is between 1 to m cross n. So consider doing a binary search 1 so on up to m cross n, and we will get a mid over somewhere here, and we should check whether and let us consider, as of now, let's consider there is a function or so there is a black box. When you give a mid over this, it will just give you an output of, it will return an output of the number of elements smaller than that mid. So let the number of elements smaller than that can be count. Yeah. So first we should find a mid such that should be always that will return a count, and for count we should check if count is equal to k, then that will be our answer. If count is less than k, that means the number of elements smaller than k or less. So we should move the low pointer to high. That is, if this is low, this is high, this is mid, then we should move the low pointer greater than mid. As the number of elements smaller than mid is less than k, we need number of the count of elements smaller than mid, which should be always equal to k. So we should move this low pointer to an element greater than mid, because this space itself will be a waste. So if number of elements smaller than this mid is less than k, which means whatever element you take between the range of 1 to mid or low to mid, it will always give a result of count less than k only. Because if there 1, 2, 3, 4, if number of elements less than 4 is less than 4 is 3, so this 1 2 3 is also waste. So when we take 2 it will be always 1, when we take 3 it will always be 2. So this whole space will be a whole range will be a waste. So we need to move low to mid plus 1, low to mid plus 1, and if it is greater than k, then same case applies, like high will become less than mid, because whatever number, if there is a 1 2 3 4 5 6 7 8, so when 4 gives 3 or k is less than 3, so this 5 will obviously give you 4, 6 will obviously give you 5, 7 will obviously give you 6. So this whole space is waste. We need to just check below 3 only, as our k is less than 3. So the count, when the count is greater than 3, the high will go less than mid. Yeah, this is the basic logic. As the arrays are sorted in this matrix, as the rows are sorted in this matrix, the simple idea is to do binary search in the range of the first element and the last element. I will explain you how the element which we take will always be inside the binary search. Will be always be inside the matrix rather than somewhere which is not present in the matrix. So as I told, so let's go for this black box stuff. As I told, this black box is going to find us the number of elements which is less than the mid we are giving in. So if there is a matrix over here from 1 to m, as it is 1 to n, as it is m cross n matrix, the first row will always contain number from 1 to n, that is 1 2 3 4 so on up to n, and the remaining rows will always contain 2 times I times the first row. So when the second row will always contain 2 cross row 1. That is, if first row is 1, 2, 3, so on up to n, second will contain 2, 4, 6, so on up to 2n. Because we know that matrix of ij is always equal to I cross j. So that's why it will. So third will always contain 3, 6, 9, so on up to 3n. So this also helps us to not find the exact matrix. We can just right away do this. So I will write a function. I'll write a function which will compute I equal to from 1 to so on up to m. So, and I will count the number of elements less than mid. First it will be 0. I want to count number of elements less than mid. So count will add up to minimum of n comma mid by I. So first I will say how this n comes. So maximum number of elements possible in an array will always be equal to n. So this is kind of a boundary case. So maximum it can be n. If it is more than n also, the maximum element possible will be always equal to n. So next is the mid by I. So what this gives us, like if there is a element y, a number y into I will give you which should be less than or equal to mid. Correct, right? Because so this y will always be 1 or 2 or 3 so on up to n. The y maximum value can be n, and the I is the which row we are searching in. So this y should always be one in the range of 1 to n. So we can straight away, it is kind of straight away find the exact count of the mid, count of the numbers less than mid. So we need to find y here. So y should be number of elements equal to mid by I. That is, let's consider in the first row we need to find some 3. So consider it. I will say with an example. So in first row we need to find, let mid equal to 3. We need to let it be a 3 cross 3 matrix. So it will be 1, 2, 3, 2, 4, 6, 3, 6, 9. So this is the matrix. We need to exactly find number of elements less than or equal to 3 in all 3 is 3. So when we take the first row, we will do mid by I. That is 3 by 1, which is equal to 3. Yeah. So as we can see, 1, 2, 3 is less than 3. Next is 2, 4, 6. So here mid is 3 by I is 2, which is 1. That is 2 alone. Because this second row is being produced from the first row, that is row 0, into that I. That I can be in the range of 1 to m. So we can straight away do it with an multiplication rather than doing a binary search in that sorted array. So that is the simple logic in this. Yeah, it is kind of a multiplication table only. So your y is 1 into I is fixed. So 1 into y should be less than or equal to mid. So when I is equal to, I will say, when I is equal to 1, it will be 1 into 1, 1 into 2, 1 into 3. When I is equal to 2, it will be 2 into 1, 2 into 2, 2 into 3, 3 into 1, 3 into 2, 3 into 3. So we should find this second element, which is largest second element, which is less than mid by I, which is less than mid by I. So as these are continuous, we can directly divide and find. As it is numbers from 1 to n. Yeah, that is the basic logic in this. So if it is sorted and discontinuous, then we need to do a binary search in each of these rows. If it is sorted and continuous, which is straight away from 1 to n, we can just directly divide by the number which the row is being multiplied and get the number of elements. Yeah, now I will show you the code and try to explain it. So first you can see the function which I wrote, that is from 1 to m, that is I am passing I from 1 to m, and I'm counting the number of elements less than each rows, and I'm returning the count. So as I already told, the range will be from 1 to m cross n, that is 1 into 1 into 1 cross 1 into m cross n, that is in this case 3 cross 3. I am doing a binary search, first finding a mid. So if mid equal to k, I told we can straight away return it. But the issue in this is, consider in first case I am getting I wanted some sixth smallest element. So sixth smallest element, that is 1, 2, 3, 2, 4, 6, 3, 6, 9. So that will consist of these 6 elements, these 5 elements, and this is exactly the sixth smallest element. So first I am doing a binary search from 1 to m cross n, that is 1 to 9. Let the mid be equal to 5. So when we search the number of elements in the array, less than 5, that will straight away give us 6. Correct, right? Because these 6 elements are less than 5. But the 5 itself is not present in the matrix. So in this case, what we need to do is we need to try to find the smallest possible element. So the smallest possible element. So in this, we can clearly see 4 to 6. This number of elements less than or equal to 4 will always be same as number of elements less than or equal to 5. In 6 alone, it changes as 6 is the next element present in the matrix. So in this case, when we consider from 6 to 9, the number of elements less than or equal to 6 will be equal to the number of elements less than or equal to 7 will be equal to the number of elements less than or equal to 8. So in some time when we get a 8, 8 is not present in the matrix. So we need to find the number, find the element which is present in the matrix, and the number which is present in the matrix will be always the smallest possible element for each k given to us. So what I'm doing is when that is less than or equal to, I'm trying to push the high to mid minus 1. I'm trying to go and search less than the mid we got. And if it is greater, I'm doing a mid equal to low equal to mid plus 1. And I'm returning low because consider some 1 to 9 and our answer is 6 or something. So we add a low here, mid here, high here, all at this place. And this is the this is exactly the count of numbers less than 6 is exactly equal to k. So what I will do is I will try to push this I to mid minus 1 and find it. So at that time, this I will go less than low, which will break the loop because our base case is low should be less than or equal to I. So which will break the loop, and this low will always stays at the answer. So this low will always stays at the answer. That's why I'm returning low. So yeah, this is the basic logic. There is similar kind of problem where these elements in each row is not continuous. At that time, we can do a binary search in each row and find the count of elements. But in this case, we no need to do, as each and every row is some integer multiplication of the first row. So when I run it, yeah, as you can clearly see, all cases pass. Yeah, this is the optimal solution also. This is the second problem. Problem number 1003. Check if word is valid after substitution. Given a string S, determine if it is valid. A string S is valid if starting with an empty string T, you can transform T into S after performing the following operation any number of times. That is, insert string ABC into any position in T, more formally becomes T left plus ABC plus T right. So this is the example given. I will try to explain it with an example given to us. So we should just check whether S is a valid string formed by this ABCs being concatenated at any point or any index in S. So yeah, ABC can be added to any index in a string and need to find whether that string is valid. So in first case, consider there is an ABC. I can add another ABC here or here or here or here. There are 4 possible chances. So let me add it in the second position. AABC will be there. BC will be there. So as you can see, this is the first example they gave. So yeah, we need to find whether this is a possible string by adding the ABC string to any possible index. Yeah. Now I'll give you some other example which is not possible. ABC is there. Another BCA is there. So ABC, this is possible, but this is not possible. This is completely reverse or something. As you can clearly see, for 1A, there will always be a following B and C. This is the main idea over here. This order doesn't change. Wherever you concatenate, this order will always be same. ABC order will always be same. Another example is, okay, so another example is AA, BB, CC. Here also the order is same, but this is not possible. As you can clearly see, if this is a six character, so there will be two ABC. I can add it here or here or here or here. Wherever I add, this won't be formed. So this will obviously this will return a no. So for a possible uh, string size greater than three, it should have a following B and C in previous. I will try to explain with the code clearly. First, I'm taking a string answer. So for each character in S, I'm pushing by the character straight away first. So if answer of size is greater than or equal to 3, and answer of size of third index from the last is A, third before index from the second index from the last is B, and first index from the last is C. I am trying to remove all these three characters from the answer whenever possible. By this, we can straight away remove all possible combinations. So I will try to show you with this current example. That is AB, ABC you keep, and there will be a C as I have added it here. So first answer will contain A, size is not greater than 3, nothing will happen. B, then 3. Now size is greater than or equal to 3, and it will check whether this three indexes are ABC. It's not ABC, so I will go to I will push next character. It will check for ABC. This three indexes. It is not ABC. Next I will push C. Now you can see the last index contains C. Before that contains B, and before that contains A. These are always continuous. Also, there will always be one ABC continuous. So consider like wherever you try to break it, when you find this ABC and remove it, you can simultaneously find next ABCs also. So that is the basic idea over here. So when these threes are present, like ABC is exactly present continuously, I will remove this. So now my string will contain AB. Next I will push C. And as these are also continuous, I will remove this. At last, I will return if answer is empty or not. So I will try to explain it with another example. So the example is ABC, ABC, AB, AB, CC. So ABC, ABC, AB, AB, CC. So first my index will be over here. The answer will contain A. Next it will go here. B, C. Up to this nothing will happen as size is less than 3. The size is equal to 3. And last three characters of the string is ABC. So I will straight away remove this. So again my answer will be just empty. So yeah. Next, I will go through this A, B, C. So this also can be added, and when it comes to C, it will be removed. Next is A, answer size is less than 3, don't care. B, answer size is less than 3, doesn't care. A, answer size is equal to 3. And in this case, it will check whether last three characters are ABC. No, it is not. Next, I will push B also. Last three characters are ABC. No, it is not. Then I will push a C. So as you can clearly see, last three characters are ABC. So I will just remove this ABC over here. Then I will add a C, and last three characters are ABC. I will remove these also. At last, this answer string will be empty. So yeah, in code also, I'm just directly pushing it, then checking whether it is greater than or equal to 3 and last 3, and I'm erasing last three characters present in the answer string and returning the answer dot size equal to 0. That is if answer string answer is empty. Yeah, this is the solution for it. And if we run it, yeah, it works. Yeah, guys, that's it for today. Subscribe for more videos continuously.